What if a ship could go over mountains? That question was once only a fantasy until Chinese engineers turned it into reality with the ship lift, a structure capable of raising vessels weighing thousands of tons to heights of hundreds of feet in just a few dozen minutes. Rivers are considered nature's highways, connecting towns, cities, and countries. But rugged terrain with rapids and dams has made travel nearly impossible. That's when the ship lift was born, combining gravity, hydraulics, and precision mechanics to open a new era of modern river transportation. In this video, Mandarin Tech will explore with you how humans turned a crazy idea into an icon of 21st century engineering, lifting ships over mountains and rewriting the limits of technology. China has emerged as a leader in construction technology, building some of the world's most advanced and ambitious lifting systems to keep rivers navigable despite massive dams. Hydroelectric dams are a huge barrier to waterways. Blocking the natural flow causes the water level upstream to rise, while the downstream level drops significantly, creating a height difference of several meters to hundreds of meters depending on the scale of the project. This disruption makes it impossible for ships, which depend entirely on the continuous flow, to move through the dam. The river is split in two, causing trade and water transport to stagnate, seriously affecting the economy of the areas that depend on the river. Traffic routes that were once seamless suddenly become dead ends. To overcome this problem, engineers invented the ship elevator, a clever and efficient mechanical solution. Unlike the waterlock system that has to operate through many levels, the elevator allows the entire ship to be raised or lowered in just one cycle. Thanks to this, giant ships weighing thousands of tons can overcome height differences in a short time, saving both time and operating costs. In reality, the idea of a ship lift is not new. The first versions appeared as early as the 19th century. But it took more than a century for humans to gain the capability to combine mechanics, hydraulics, and automatic control systems to make it work on a scale of thousands of tons. So how can a single system lift such a massive weight with such precision? And why are modern ship lifts safer, faster, and more sustainable than traditional locks? The answer lies in the evolution of engineering, where the ship lift is seen as the next stage of innovation in hydraulic infrastructure. Imagine a ship lift as a gigantic platform capable of raising or lowering an entire vessel, much like an elevator in a skyscraper. To achieve this, the entire foundation area must first be surveyed and reinforced with a deep system of concrete piles reaching hundreds of feet into the ground, strong enough to support thousands of tons of steel and water. Next, the water guide walls and the lift shaft are constructed with reinforced concrete in multiple layers, ensuring resistance to hydrostatic pressure and fluctuations in water level. Supporting columns and guide rails are installed in parallel to keep the lifting chamber perfectly stable during its vertical motion. The system of supporting columns and guide rails is installed in parallel to keep the lifting chamber moves with absolute stability along the vertical axis. The next stage is the construction of the lifting chamber, a massive steel tank capable of holding both the vessel and the water. This chamber is tightly welded and equipped with hydraulic gates, a balancing float system, and specialized safety devices. Dozens of high-tensile steel cables and counterweights are symmetrically arranged on both sides, connected to a central drive shaft powered by high-capacity electric motors or hydraulic cylinders. The entire movement is monitored from the central control room, where hundreds of sensors measuring pressure, tension, and tilt continuously transmit data to the control software, ensuring that the lifting chamber operates smoothly and in perfect synchronization. However, to bring such a massive structure into stable operation, engineers must confront a series of challenges related to structure, environment, and precision. One of the most notable issues is thermal deformation. When sunlight heats one side of the tower more than the other, the steel expands unevenly, causing slight deviations in the guide rails. It may sound insignificant, but in a system weighing thousands of tons, even a deviation of a few thousandths of an inch can affect balance, leading to vibration or jamming during operation. To resolve this, engineers designed an automatic thermal compensation system, combined with deformation sensors along the tower's body that make real-time adjustments, ensuring absolute stability even as the temperature changes throughout the day. In addition, vibrations from the motors, fluctuations in hydraulic pressure, and strong winds can all affect the cable and counterweight systems. For this reason, the entire structure is equipped with mechanical dampers and undergoes regular inspection cycles to monitor material fatigue, ensuring that every component operates within safe limits. Maintaining perfect synchronization among dozens of massive load-bearing cables under heavy loads and harsh weather conditions is the greatest challenge and also the clearest proof of the sophistication behind modern ship lift engineering. To truly understand the engineering power behind these colossal structures, let's take a look at how a ship lift actually operates. Many people describe them as a form of mad engineering, not only because of their massive size but also due to the precision required to lift a vessel that is floating in water. Simultaneous control of Archimedes' thrust, buoyancy, and displacement requires absolute precision in calculation. Essentially, a ship lift works like a gigantic elevator, except instead of lifting people, it lifts an entire ship along with the surrounding water. When the ship enters the lifting chamber, which is about 40 meters long and 12 meters wide, the stabilizing system keeps the vessel fixed at the center position. Then, massive steel gates close, isolating the chamber from the external river, and water is pumped in to create a balanced floating state. At this point, 256 steel cables are simultaneously tensioned, connected to a system of gears, racks, and hydraulic pistons to raise the chamber vertically. The entire process takes about 30 minutes, lifting the vessel to a height greater than the Statue of Liberty or the Pyramid of Giza. This structure is equipped with the world's first gear and screw shaft safety mechanism, capable of withstanding earthquakes up to magnitude 8, strong winds, and large waves, while maintaining precision within 10 millimeters. The counterweights and hydraulic pumps operate in perfect synchronization to reduce load on the system, ensuring completely stable and smooth motion. During the lifting process, operators monitor the chamber through observation windows and a central control panel, ensuring that all parameters remain within safe limits. When the chamber reaches the required height, the upper gate opens, allowing the ship to leave the chamber and enter the upstream reservoir to continue its journey. The lowering process for downstream vessels follows the same principle. All operations are based on the same balance, precision, and safety maintained to an almost absolute degree. Safety is the supreme priority in every ship lift system. Immediately after completion, the entire structure must undergo a rigorous load testing phase, using simulated water tanks to check balance, vibration, and braking accuracy. Each test is monitored by vibration sensors and deformation measurement systems to ensure that the structure can withstand loads of thousands of tons while still operating smoothly. From foundation treatment to the final calibration stage, the construction and commissioning process can take between 5 and 8 years, a testament to the combination of engineering power and human control over massive volumes of water. According to many reports, the investment cost for a modern ship lift system can reach billions of yuan, clearly reflecting both its technical complexity and its strategic importance within the national transportation network. In the event of a cable break or motor failure, automatic mechanical brakes are immediately activated to hold the chamber in place. These braking units are powerful enough to secure the entire lifting chamber, weighing thousands of tons, even during a complete power outage. In addition, the overall structure is reinforced to withstand strong winds, heavy rain, and extreme temperature variations. Each system follows a strict maintenance schedule, operating around 22 hours per day and dedicating several weeks each year to inspection and component replacement before any signs of wear appear. This process ensures that the ship lift remains stable, continuous, and safe throughout decades of operation. Around the world, many large-scale projects have proven that the concept of allowing ships to climb mountains is no longer a fantasy, but a tangible achievement of 21st century hydraulic engineering. Among them, the ship lifts in China, particularly the Three Gorges and Gupitan, are regarded as true marvels of engineering and construction management. The most remarkable is the Gupitan ship lift, one of the most ambitious projects ever built. This system is divided into 3 independently operating stages, which increase vessel traffic speed and significantly reduce waiting times. The first stage provides a lifting range between 72 and 79 meters, depending on the downstream water level. The second stage offers a fixed lift of 127 meters, serving as the main section of the system, and the third stage operates in the opposite direction, capable of lowering vessels up to 47 meters, depending on the reservoir level. In Europe, the Strepitieux boat lift in Belgium is considered an iconic structure. With a lifting height of 73.15 meters, it once held the record as the world's tallest ship lift. It features 2 independent lifting chambers, each 112 meters long and 12 meters wide, can hold ships weighing up to 1,750 tons, moving vertically thanks to a balanced counterweight system. The project took nearly 20 years to complete and is part of Belgium's waterway modernization program, a small nation with a long-standing tradition in hydraulic engineering. In Germany, the Scharnebeck twin ship lift, located near the city of Lüneburg in Lower Saxony, is one of the largest twin ship lifts in the world. Completed in 1974 and operational since 1975, the system allows vessels to overcome a 38-meter difference in elevation on the Elbe lateral canal. Each lifting trough operates independently, carrying a total load of up to 11,800 tons, a testament to Germany's exceptional mechanical design and precision in weight balancing. In North America, the Peterborough lift lock in the city of Peterborough, Ontario, Canada, stands as one of the earliest and tallest hydraulic ship lifts in the world when it was completed in 1904. This system raises vessels through a height difference of 19.8 meters using the principle of gravitational balance. 2 water chambers sit on giant hydraulic cylinders, with the heavier chamber forcing water through a pipe to lift the other chamber, creating smooth motion without the need for motors. These engineering marvels not only demonstrate mechanical power, but also bring tremendous economic value to the regions they serve. Thanks to the emergence of shiplift systems, massive vessels can now traverse steep rivers and dams that once divided trade routes, transforming remote inland areas into dynamic links within the national transportation network. A shiplift can be considered a representation of the pinnacle of hydraulic control and modern structural engineering, a symbol of how humanity transforms geographical challenges into opportunities for development. Instead of relying on a series of traditional waterlocks, this system can lift an entire ship, along with thousands of tons of surrounding water, to heights of hundreds of feet in just a few dozen minutes. Such structures not only redefine river transportation, but also reflect the technological capability of our era, where steel, water, and algorithms work together to shape the future. A ship lift is not a static structure, but a living system, operated through data, sensors, and human intelligence. And if you wish to continue exploring how technology and humanity together are rewriting the limits of our world, don't forget to like and subscribe to Mandarin Tech, where technology is not only told, but seen as a true advancement of humankind.